So we've been given this function and we're asked to find the x coordinates of the stationary points. Stationary points is a differentiation technique, so we're going to start by taking the derivative of this function. So notice that the function is given in terms of y, so our derivative will be notated dy dx. If it was given as f of x, then we would use the f dash x notation for the derivative. So we need all of the terms to be in a differentiable form. So the form for the power rule, which is what we're going to use, is ax to the n. So each of those terms is in that correct format. So they're all differentiable in the form that they're in. That's a really important thing to check. So we're using the power rule, which has multiply by the power and reduce the power by 1. So 4 times 1/2 gives us 2. X, take 1 off the power to go down to 3. For the next term, 3 times minus 2 gives us negative 6. X to the power of 2. And a constant term, like a 6 or any other number, differentiates to 0. So that's just going to disappear when we take our derivative. So we've got our derivative. How are we going to use that to solve the problem? Well, the key fact is that for the stationary points, so just abbreviate that to SPs, and this is an important line of working to get in there. For the stationary points, the derivative, in this case dy dx, or f dash x if you're using the other notation, equals 0. That is the absolute key. So at the stationary points, the derivative equals 0. You need to get that line of working in there. That just tells the marker what you're going to do in the next line, which is to take your derivative and set it equal to 0. So we get 2x cubed minus 6x squared equals 0. If we can now solve this equation, then we will have found what we're looking for, which is the x coordinates of the stationary points. This is a polynomial type equation. Usually these are quadratic equations. In this case, it's got an x cubed, so it's a polynomial equation. But regardless of whether it's a polynomial or a quadratic equation, it needs to be factorized to be solved. In this case, we're going to factorize using a common factor. The highest common factor here is 2x squared. So 2x squared goes outside our bracket, then just trying to figure out what goes inside. So we'll need an x here, and we would need a negative 3 here. Separating these into two separate equations, we get 2x squared equals 0, and then we get x minus 3 equals 0. Just like we do for polynomial or quadratic equations, factorizing and separating them into multiple equations. This one, we can divide both sides by 2 and then square root, but basically the answer is going to be 0. In fact, anytime you've got a common factor in your factorizing, the solution to that common factor part will be 0. This one is trivial to solve to give us x equals 3. And we're done at that point. So there's no finding the y coordinates that goes with those points because we weren't asked to do that in the question. There's no determining the nature of the stationary points, which we're sometimes asked. So there's no need for a nature table or anything like that. That is the end of that question. We've been given this quadratic equation and we're asked to find the possible values of k. So first of all, notice the question mentions values, plural. That tells us we're looking for more than one solution, and it's also going to inform how we go about the working. The question also tells us that this quadratic equation has got equal roots. So equal roots is another way of expressing one real root. So the important point there is first of all to know the terminology. That basically is one real root, and the important thing with roots is to connect them to the discriminant. So root questions, information in the question about roots is to do with discriminant. So equal roots implies that the discriminant b squared minus 4ac is equal to 0, okay? So that's the first thing, that's going to be our starting point. So let's identify our a, b, and c values. So the a is the coefficient of the x squared term, which is 1. The b is the coefficient of the x term, which in this case is everything in front of the x, which is k minus 5, and the c value is just everything that's not the a and the b value. In this case, it's just the number 1. So we can plug this into our discriminant. So we're going to get b squared minus 4ac is equal to b squared, so k minus 5 squared, so it needs to be k minus 5 all squared. So we use a bracket for that, that's quite common in these questions, minus 4 times the a value, which is 1, the c value, which is 1. It's good practice maybe just to use little brackets for those. And we already know we can set that equal to 0 because we know that the quadratic equation has got it's got one real root or equal roots. So we just need to solve this equation now to get our value or values of k. The fact that they said values tells us it should be a quadratic equation, and it looks like it is going to be explicitly a quadratic equation in a moment. So we're going to go ahead and multiply out the bracket. So you might just want to write that bracket down twice. If you're very experienced with multiplying out a single bracket with a squared on it, That's fine. If you're less confident, maybe just write the bracket down twice. We can process this term. 4 times 1 times 1 is just 4. Keep that equal to 0. Multiplying out the bracket, you would get k squared. You would get two negative 5k's, which will total to minus 10k. And then minus 5 times minus 5 is plus 25. Keep the minus 4 on the end like this. And we're just basically trying to form this into a trinomial. So k squared minus 10k, these combine to make a plus 21. Trinomials are not always students' most favourite things, especially factorising them. But the fact is that if you get a trinomial and you need to factorise it to solve an equation, it kind of validates whether your working up until that point is correct. In other words, if this quadratic equation, this trinomial factorises, we're on track. If not, then we've probably done something wrong. So we're going to need a k and a k. To make a 21, we'll need a 7 and a 3. 7 and 3 can combine to make a 10. In this case, we need a minus and a minus, so they multiply to make plus 21. They combine to make minus 10, so we're done with the factorising. So we can separate these into two equations. So k minus 7 equals 0. K minus 3 equals 0. This is always what we do with quadratic equations. And then we get solutions. K equals 7. And for this one, k equals 3. Sometimes it can confuse students, the fact that we started off with a quadratic equation and we've got this second quadratic equation, but that is just the one that represents a discriminant, so they're kind of in a way two separate, well, they are two separate things. That is the end of that problem. In this question, we're being asked to find the equation of the circle C2. If you're ever asked to find the equation of a circle, you're going to want to use the basic form of a circle equation, which is on the formula sheet. So it's x minus a squared plus y minus b squared equals r squared, where AB is the center point and r is the radius. There is a general form of a circle equation as well. That's not the one to use if you're making the equation of a circle. So in this question, we're told the equation of circle C1, and we're told that the radius of C1 and the radius of C2 are the same, and we're given the center point of circle C2. So it's C2's equation we're trying to make. We've already got the center point, so that means we've already got our a and b values. So the only thing we actually need really to solve this problem is the radius. It's the radius and the center point that define a circle. So if you're ever trying to make the equation of a circle, those are the only two things that really you need to find. The end part, plugging into the formula, is always quite easy. So we just need to find that radius. We're going to turn our attention to circle C1 because we're told that the two circles have got the same radius. So if we can find the radius of circle C1, then we can just transfer that radius to the circle C2. So there's different ways to do this, but remember that the radius formula is on the formula sheet. So for the general form of a circle, the radius is given by g squared plus f squared minus c. So this value here, minus 6, represents 2g. So you can write 2g, and you can copy this from the formula sheet. 2g equals negative 6. That means that g is going to equal negative 3. And similarly, this value here, the negative 2, represents 2f. So 2f equals negative 2, given f equals minus 1. Be careful not to get those confused because they do not go in alphabetical order. So it's g first and then f. Why that's the case, I don't know. It seems a little bit crazy really, but it is in non-alphabetical order. These guys obviously are in alphabetical order. So don't know who came up with that. It's kind of crazy. Anyway, we've now got the values that we can plug in here. The c value, by the way, is just this number, negative 26. So we can make our radius of C1 by going square root of minus 3 all squared plus the f squared, which is minus 1 all squared. And the formula demands minus c, so it's going to be minus 26. So watch out for double negatives there. So if we just go ahead and process that, we're going to get the square root of, this is 9, this is 1, so adding those together we'll get 10. This is minus minus, which is a double negative to give us plus 26. Adding those together, we're going to get the square root of 36, which is 6. The fact that that's come out to be a square rootable number to give us a whole number solution or radius, that is quite reassuring. It doesn't have to be a whole number, but it kind of suggests we've probably done it right. We know the two circles have got the same radius, so we can write in the circle of circle C2 has got a radius of 6 as well. So now we've got all the bits that we need. So this is our A value, this is our B value, and we can just plug in. So the final form will be x minus A, which is 4, all squared, plus y minus b. B is minus 2, so it's going to be minus 2. That's going to be a double negative. Watch out for those in circle equations. So it'll be y plus 2 all squared. And then 6 squared, so just writing that as either 6 squared or preferably writing it as 36. So that is the solution for circle C2. We've been given this recurrence relation and we're told that the first 3 terms generated by that recurrence relation are 6, 9 and 11. But whereas we normally have a numerical value here and here, we've been given the variables m and c, and in the first part of the question we're asked to find the m and the c values. So remember that recurrence relations need labels on the terms, so we could label these terms as u1, u2 and u3. So I'm going to say let u1 be 6, you can make this u0, I'm going to go for u1. U2 would then be the second term, which is 9, and the third term, U3, is 11. So a recurrence relation, remember, is just a formula, a rule if you like, that generates a sequence of terms where each term is based on the previous term. So if you've got U1 here, this would need to be U0. If this is U5, this is U4. So this number should always be 1 fewer than this number. So what we're going to do here, we're going to just plug these terms into our recurrence relation. You can only plug in 1 and 2. You can't plug in, for example, 1 and 3 because there's more than a 1 gap between the two subscripts there, but you could use 2 and 3. In fact, we're going to use both. We're going to start with 1 and 2. So I'm going to take my recurrence relation and rewrite it as u2 equals mu1 plus c. So just putting in specific terms rather than these general terms, and that's fine as long as this number, like I say, is 1 fewer than this number, or the other way around, this number is 1 more than this number. But we can actually take these terms and put them in. So u2 is 9, so we get 9 times m times u1. Well, u1 is 6, so that's going to be m times 6, which I'm going to write as 6m plus c. And that's basically all we can do with u2 and u1. Going to do the same thing now with u3 and u2. So the bigger subscript always goes on this side. So u3 is going to equal m times u2 plus c. Again, just keeping that difference of 1 between those subscripts. So plugging in our numbers for u3 and u2. So we get 11 equals m times u2. u2 is 9, so that's going to be 9m plus c. So what have we done there? Well, we've used the information first of all, but we've basically generated simultaneous equations, haven't we? So we can go ahead and solve these. So let me just take these two and put them together. So I'm going to write it as 11. I'm going to put this one first. So 11, doesn't matter the order. I'm going to go with this one first because the bigger numbers are usually better to get on the top equation. So we can call this equation 1. So this is equation 1. And then I'm going to use this one as equation 2, which is going to go underneath equation 1. So it's going to be 9 equals 6m plus c, so 6m plus c. So casting your mind back to how simultaneous equations work, we add or subtract the equations to try and eliminate one of the variables. These variables are kind of matched up. They're both 1c. These are not matched up. So we're going to focus on eliminating the c, and we can achieve that just by subtracting our two equations. So if we go ahead and subtract in the columns, 11 minus 9 is 2. And then here we get 9m minus 6m to give us 3m. And the c's go to 0. They eliminate, so we don't need to worry about writing that in here. Solving this equation, we would just then divide both sides by 3 to get m equals 2 over 3. We then just take this value and substitute it back into one of our equations. It doesn't matter which one you go for. I'm going to go for this one. I'm just going to write it the other way around. So I'm going to write it as 6m plus c equals 9, just to put the variables on the left, which is what we're more used to. We're going to replace our m value by 2 over 3 because we now know that the m value is 2 over 3. So this becomes 6 times 2 over 3 plus c equals 9. Multiplying these together, so 6 times 2 is 12, divided by 3 is 4. So we get 4 plus c equals 9. Solving this little equation by subtracting 4 from both sides, and we get c equals 5. So our two values for m and c are m is 2/3 and c is 5. And that's part A of the question. In part B of the question, they're asking us to then make the next term in the sequence, the fourth term. So we can go back to our recurrence relation and populate it with the m and the c value. So we can update our recurrence relation. So we now know that it's un plus 1 equals the m value, which is 2 over 3, times un plus the c value, which is 5. So this is now our actual recurrence relation. If you want to make the term u4, that would be putting a u4 here, then that's fine as long as this term is u3. And fortunately, we know what u3 is, it's 11, so we can go ahead and plug that in. So we're going to get u4 equals 2 over 3 times 11 plus 5, and then it's just a little bit of numeracy really to work this out. So if you're timesing a whole number to a fraction, you just multiply it to the top, so that's going to be 22 over 3 plus 5. A little bit of work here to do, so we want to make that 5 into a fraction. It's got the same denominator as the other fraction. So the 22 over 3 we're just going to leave. The 5 we're going to write as 15 over 3. 15 over 3, 15 divided by 3 and 5 are the same thing, just written in a different way, but the important thing is these have now got a common denominator. We can go ahead and add those together to get 37 over 3, and that's the end of that problem. We've been given these 3 points and we're asked to show that they're collinear. Collinear is just a fancy way of saying that they lie in a straight line. This question can be done by gradients or by vectors. I'm going to do by vectors, which is a more common approach with these questions, especially if the points are given in three-dimensional space. So we need to start this question by making the appropriate vectors, which is pretty much always going to be in alphabetical order. So I'm going to make vectors AB and then BC. That's not always true, but the thing that is always true, you want to make your vectors going from one of the end points to the middle point, and you can see by the coordinates 1, 4, and 8 that this is the middle point, and then the other vector from the middle point to the other end point. So in other words, we need to make vectors A, B, and BC, but it is usually the case that these questions are designed so that that is in alphabetical order, but not always. That's not always the case. So the vector AB, how do you get from A to B? So you move 3 in the x direction, you move minus 6 in the y direction, and you move positive 3 in the z direction. Notice that there's a common factor there with the elements of that vector, so I'm going to pull that common factor out, which you don't have to do, but I think that is good practice. It's a common technique, so looking for that common factor, and that kind of validates that you've done it correct, because there should be, in most cases, a common factor. So making the other vector, the vector BC, just doing the same thing. The vector BC, remember, is asking the question, how do you get from B to C? So you move 4 in the x direction, and then from minus 1 to minus 9 is a move of negative 8, and then 0 to 4 in the z direction is a move of positive 4. Notice again we've got a common factor, this time a common factor of 4. Again, that helps to kind of validate that you've done the work incorrectly, but what massively validates that is the fact that these base vectors have come out to be the same. That should always be the case in a collinear point question. So how do we go about showing that it's collinear? Well, we're going to show that these two vectors are parallel, and since B is a common point, if you've got two parallel vectors, which I will demonstrate with my pens, if these are your two vectors, A, B, and BC, if they're parallel like this, well, parallel is also like this. It can be like this, that's also parallel. But if this is point B and that's also point B, then they can't be like this, can they? They've got to be here. So if they're parallel and there's a common point, then the points are collinear. So B is clearly a common point. It's a midpoint of the 3 points, A, B, and C. Are they parallel? Well, you can show that they're parallel by showing that one vector is a multiple of the other. If you multiply this vector by 4, then this would be 12 times 1 minus 2, 1. If you multiply this one by 3, this would also be 12 times 1 minus 2, 1. So in other words, 4 times the vector AB equals 3 times the vector BC. That's good enough to show that they're parallel. You can make it more explicit by changing the sort of subject of the little equation to one of the vectors. So AB equals 3 divided by 4 BC, and any vector which is a multiple of another vector, that shows that the two vectors are parallel. So these vectors are parallel. You would need to make a statement, something like, so this implies that the vectors are parallel. You would want to write that out more fully. I'm just going to save a bit of time, but this implies that they're parallel, and this is a key point, and since B, point B, is a common point, then A, B, and C are collinear. So one big mistake that a lot of students make in this question, they'll get the working right, but at the end there, when they're making their statement, they'll say, therefore, vector AB and vector BC are collinear. But it's not the vectors are collinear, it's just that we're using vectors to show that the points are collinear. So be careful with that sort of trivial mistake that sometimes comes up in this question. So this is part A of this question. Part B is to state the ratio in which B divides AC. So you can imagine that if you've got points A, B, and C, something like this. So A and C is the endpoint, A and C are the endpoints. Wherever point B lies, let's just say that point B lies somewhere here. It's going to be in some ratio between A and C. So it could be the ratio is 1 to 2 or something like this. This question can cause a lot of confusion. It's only a 1-mark question, but I'll give you a little trick. If you write this part here, which you will need to write as part of the working to show they're collinear, if you write it in order left to right, or in order alphabetically usually, then you just need to spin these numbers around to get the ratio. So notice that the question is worded state. In other words, there shouldn't be any working in this question. This is where you get it from. You just take these two numbers and spin them around. So the ratio is 3 to 4. You can elaborate on that, but there's no need to. As long as you get that line correct, you just spin those numbers around and that will give you the ratio. In this question, we've been given this function and we're asked to find the derivative dy dx. So anytime you're asked to find a derivative, you've got to ask yourself, is the function in a differentiable form? And it depends which rule you're going to be using as to what that form looks like. If you're using the power rule, then you want the terms in your function to be in the form ax to the n. So for example, something like 3x to the power of 4. This one's not that rule, this is going to be the chain rule. And the chain rule can take on some slightly different forms, but generally it's in the form ax plus b to the power of n, or thereabouts. Not exactly that form, but something like that. But the thing it cannot be is in a fraction form like this. So in other words, this bracket is in the wrong place. It needs to be up on the top. So that's the first thing with any differentiation question, and it applies here because this is in a non-differentiable form. I'm going to fix that by bringing this to the top using a indices rule, which just says you can bring it to the top, but you make the power the negative of what it currently is. So that power of 5 on the denominator becomes a minus 5 when you bring it up to the top. Okay, and that is our y function. So this is now in a differentiable form using the chain rule. So we can go straight now to the derivative dy dx. Chain rule can be a little awkward, but it really just means taking two derivatives and multiplying them together. Sometimes the chain rule is massively overcomplicated. It's actually for differentiating composite functions, a function inside a function. Well, we've got the function 1 minus 3x inside this exponential function. So these are our two functions, but basically in this scenario, we take the derivative of the whole bracket, if you like, using the power rule. That says multiply by the power, so bring the minus 5 in front basically. Leave the bracket alone, take 1 off the power, so that goes to a negative 6. That's the power rule. The thing that makes it the chain rule is on that same line of working, now multiplying, which I'm going to use a dot to represent, the derivative of the inside of the bracket. The derivative of 1 minus 3x is negative 3. So we're going to multiply by negative 3 like that. So one derivative, second derivative, multiplying them together. Almost done at this point. The only thing we can do is tidy up. So we can tidy up by multiplying these together. That's going to be a double negative to give us a plus 15, positive 15, and then we've got our bracket. And anytime you do a derivative or an integral, and the answer comes out to be a negative power, either on an x term or on a bracket like this, you're going to want to rewrite that with a positive power. So bringing this back to the bottom of a fraction, so the opposite of what we did here, so kind of going from this point back to this point, just by introducing the fraction, the 15 will just be parked on the top of the fraction. So it'll just be 15 over the bracket 1 minus 3x, all of that to the power of positive 6. And that is our derivative. In this question, we're asked to find the equation of the line that passes through the point 0, minus 4 and is perpendicular to the line L. So because we're trying to find the equation of a straight line, we're going to use the formula y minus b equals mx minus a. And to use this formula, we really just need an m value and a point AB. So that's what we're trying to track down to be able to answer this question. So a point on the line and the gradient of the line. The point on the line we've already been given, that is the point 0, minus 4. And that's quite often the case in straight line questions. You're given a point on the line, any point on the line will do. So our challenge here really is to track down the gradient. So we're told that our line is perpendicular to a line L, which is making an angle of 30 degrees with the x-axis. So there's a little formula that connects gradient and angle together. So that is given by m, the gradient, equals tan of the angle theta. And theta is the angle with the positive direction of the x-axis. So if your x-axis goes this way and your line goes this way, so let's say this is our line L, then this is where your 30 degrees would be. So that's the kind of scenario we're dealing with here. So we know the angle is 30 degrees, so we know the gradient of this line is given by the tan of 30 degrees, the tan of the angle. So the tan of the angle, 30 degrees, we need to do non-calculator, so this is trigonometric exact values. This one you should really just know off the top of your head. So the tan of 30 degrees is 1 over root 3. Or you could rationalize that to make it root 3 over 3. So I'll just put that in a bracket, that's another option, root 3 over 3 like that. So now we've got the gradient, but it's not the gradient of our line, it's the gradient of the line that's perpendicular. So I might just clarify this by putting a subscript L on these. So that's the gradient of the line L. We're interested in the gradient of the line perpendicular, so we can maybe call that M perp, just to suggest that it's perpendicular to the line L. And remember, the rule for this is if you've got two perpendicular lines, their gradients multiply together to make minus 1, or we can think of it as being the negative reciprocal of this. In other words, a reciprocal means you flip it and you apply the opposite sign. So to flip 1 over root 3, we're going to get root 3. This is positive, so we would make it minus, so minus root 3. And if you multiply those together, you would get negative 1. That's a rule. The gradients multiply to make minus 1 if the two lines are perpendicular. So this is our gradient. So we can put this, transfer this information over here, so minus root 3. Okay, so now we've got our everything we need, we can just plug those into the equation. Plugging into the equation is fairly straightforward, although it is kind of unusual in this case to have a root for the gradient. Normally the gradient is just a whole number or a simple fraction. So this is our a, b, and this is our m. So we're going to get y minus 4, so you maybe just write that with a bracket initially, equals the gradient, the m value, minus root 3, bracket x minus 0. So having that 0 is going to make things a little easier. Minus 4 is plus 4, so that becomes y plus 4. X minus 0 is just x, so minus root 3 times x is minus root 3x. Okay, and then just moving the 4 to the other side to put it in the correct format of a straight line, the y equals mx plus c format. So y equals minus root 3x minus 4. And that's the final answer. That is the equation of the line. Looks a little bit odd having the gradient minus root 3, but that's just the way this question's come out. Y equals mx plus c. So we're good to go, and that is the final answer. In part A of this question, we're asked to set up an integral that represents a shaded area between these two curves and between the points of intersection -1 and +2. So we're not asked to evaluate that integral, just to set it up in part A. So we're going to set up the integral between -1 and 2. So remember, going in numerical order from the lower limit to the upper limit, so -1 to 2, of the upper function minus the lower function. Remember, it's the upper function on the shaded area minus the lower function. This is our upper function in this case, and the lower function. So good practice, in fact really important to use brackets here. So upper function is x squared plus 2x plus 3 minus the lower function 2x squared plus x plus 1, and we're integrating in the x direction, so dx. So we're almost done at this point. We just need to basically tidy up the terms. So it's only a 1-mark question, not a lot of work to do in this one. Just knowing this sort of formula really. So x squared minus 2x squared is negative x squared. 2x minus x is plus 1x. 3 minus 1 is 2, so plus 2, and keeping our dx on the end. So it's super important to use these brackets, particularly for the second term, second set of terms, because we're taking all of that away. So the minus is applying to all of those. So that is part A done. In part B, we want to evaluate that integral, which represents the shaded area, to then find the shaded area. So I'm just going to transfer this over here. So it's the integral between minus 1 and 2. Remember, this is going to be a definite integral. It is a definite integral, so when we evaluate it, we need to think in terms of a definite integral. That means there's going to be no plus c, for example. We don't need the constant in a definite integral. And when we evaluate this, remember the solution, if you like, or the terms integrated, are going to go inside the square bracket. These terms are all ready to use the power rule. They're in the correct format, so we're going to increase the power by 1. So that goes up to a power of 3, divide by that new power, just using the power rule. Remember that an x on its own is secretly an x to the power of 1, so that's going to be x to the power of 2 by increasing the power by 1 and dividing by 2. A constant term like a 2 integrates to 2x, or if it was a 5, it would integrate to 5x, etc. So moving the limits over to the right hand side, so like I said, no constant required for this. And now we just need to evaluate this by subbing in the upper limit first and then subtracting from that the lower limit subbed in. So really important to use brackets here. So putting in the 2 first, 2 cubed is 8, so that is minus 8 over 3. 2 squared is 4, divided by 2 is 2, so I'm just going to go straight to doing that. You can write that in if you wish. You can write a line to write 2 squared divided by 2. I'm just going to save a bit of time by processing the numbers as much as I can as I go. And then 2 times 2 is 4, so that is just a 4. Subtracting from that the minus 1 limit subbed in. Be careful with the negatives here. So minus 1 cubed is minus 1, but there's a minus in front of the fraction, so that's minus minus 1 to give you a plus 1, otherwise just known as 1. So that's going to be 1 over 3 for that one. So quite easy to get that one muddled, and then minus 1 all squared is positive 1, so it's going to be plus 1 over 2, and then 2 times minus 1 is just negative 2, like that. So at this point we're well on our way. There's just a little bit of numeracy now. It can be a little tricky. Personal preference as to how you do this. If it was a calculator question, just put it in the calculator. But looking to simplify the terms quickly and efficiently, I like to try and look for terms that have got the same denominator. So minus 8 over 3 minus 1 over 3, that is minus 9 over 3, but 9 over 3 is just 3. So when you combine these terms, you just get negative 3. I'm just going to tick these off as I go along. 2 plus 4 is 6. I might just leave that as a 6 by combining those numbers. And then we've got minus 1/2. And we've got minus minus 2, which is a plus 2. So it's up to you if you want to do it that way. The reason why I like to do it like that, now we've gotten rid of some of the fractions, so we can combine these whole numbers. So 6 plus 2 is 8, minus 3 is 5, so this becomes 5 minus 1 over 2. And yeah, and just taking that forward, so it's up to you how you want to finish this off. I mean, that's going to be 5 minus 1/2, 4.5. Using a mixed number, or you could use a decimal 4.5. If you wanted to use it as a fraction, then the 5 would have to become 10 over 2. So 10 over 2 minus 1 over 2 gives us 9 over 2 or 4.5. It's up to you. But because we've just found an area, we need to express the units, which are just a generic unit. So unit squared. There's no particular units in this question, so we're just leaving that area as unit squared. So that is our shaded area between the two curves. In this question, we've been given these two vectors u and v, which look a little unusual because they've got these variables in them. And in the first part of the question, we're asked to find u dot v. So u dot v is the dot product. There are formulas for this on the formula sheet. There's a couple of different options. We're going to use the option where we just multiply the corresponding components together. So we can make, so this is part A1, we can make the product u dot v just by multiplying the first element to the first element, and then adding these guys multiplied, and then adding to that these guys multiplied. Notice in the question they've said that the u dot v should come out to be an expression rather than a number. That means it's going to have variables in it. The variable is obviously going to be p. Normally the dot product comes out to be a number, or most of the time it's a number. So picking up on that keyword expression helps validate that you've got the correct sort of solution. So if this came out to be a number with no variable in it, but the question said it should be an expression, then something's gone wrong there. So we're going to do p times 2p plus 16. So I may just write that one. So it's going to be p bracket 2p plus 16. So multiplying those together. And then we're going to add to that negative 2 times negative 3. It's a double negative, so it's just going to be positive 6. And then 4 times 6 is 24. So we can go ahead and multiply those like that. Now we're just going to tidy this up. Just to save space, I'm just going to pull my equals over here. In fact, no, let me just pull it down to here actually. So 2p times p is 2p squared. P times 16 is 16p, and then we've got our plus 24 on the end. So that is us done at that point. That is just to make the expression that represents u dot v. We're then asked in the next part of the question, so part A, 2, to find the value of p for which these two vectors are perpendicular. So there's a key fact you need to know here connected to the dot product. This is why they've asked us to make the dot product. And the key fact is that if they're perpendicular, so perpendicular, that implies that the dot product, u dot v, so remember with vectors to put your little lines underneath, u dot v equals 0. So this is the key fact that we're going to use. So we know that if they're perpendicular, u dot v is 0, but this here is u dot v. So we can say that the u dot v, which we're representing as the expression 2p squared plus 16p plus 24, that must be equal to 0 if the vectors are perpendicular. And it's asking us to find the value of p. If you want to find a value, you need an equation. To find a value, generally, this is an equation, it's a quadratic equation, so now we just need to solve it to get the value of p. In fact, I should really just clarify, in the question it actually says values, plural, so we're looking for probably, well, two values. Two values is good because we've got a quadratic equation that should give us two values, two solutions. So look for those singular or plural clues in the question. So we need to factorize this, but there's a common factor of 2. We could just divide everything by 2 to make it easier. So this becomes just a p squared, this becomes an 8p, and this becomes a 12. 0 needs to be divided by 2 as well, but 0 divided by 2 is 0. Hopefully this will factorize. You know, trinomials are good because if they are correct, then they should factorize in this scenario. So we need a p and a p. To make the 12, we're going to use a 6 and a 2. Could use a 4 and a 3, but 4 and 3 doesn't add to make 8. 6 and 2 does, so it factorizes like this. Separating these into two equations, we're going to get p plus 6 equals 0 and p plus 2 equals 0. And then just solving these little linear equations to get p equals negative 6 and p equals negative 2. So really that question is just about knowing the key fact that the dot product equals 0 if the vectors are perpendicular. The next part of the question, part B, is a little trickier, but again it hinges on knowing a key result. If you've got two vectors that are parallel, then one is just a multiple of the other. So for example, if you had a vector A, which was parallel to some vector B, then you know that one of the vectors is a multiple of the other. So it could be that A is equal to something like 3 times b, or 1/2 b, or 10 times b, but there's got to be scalar multiplication between the two. In our question, we know that there's going to have to be some multiple between u and v. So if you take u and multiply it by some number, it should give you v, the terms, the elements in v, if they are parallel. So let's just look at that. What would we need to multiply 4 by, for example, to get to 6? Well, not obvious, but it would be 1.5, wouldn't it? Or 3 over 2. Let's check if that works here also. So if you multiply 2 by 3 over 2, or 1.5, you do get 3, including the minuses. So the multiplication factor here is 1.5, or 3 over 2. So that tells us that if you take vector u, and if you multiply it by 3 over 2, so 3 over 2, or 1.5, that's going to give you vector v. So that's not easy, but that's resting on the fact that if they're parallel, they've got a scalar multiple between them. The scalar multiple is 3 over 2. One vector is 1.5 times the other vector. But this has to be true. This has to be true for all of the terms. So it's true that if you multiply 4 by 1.5, you get 6. If you multiply negative 2 by 1.5, you get negative 3. But it should also be true that if you multiply p by 3 over 2, you get 2p plus 16. It's got to be consistent between all of those. So that's what we're going to do. We're going to say that if we take p and multiply by 3 over 2, so it's going to be 3 over 2 times p, that should equal the corresponding term in the other vector, the other element, which is 2p plus 16. And basically that gives us an equation to solve to get the p-value, in the same way that we formed an equation here by making the dot product 0. So just going ahead to solve that equation, we could start by getting rid of the fraction, multiplying everything by 2. If we multiply this by 2, we're just left with 3p, multiplying this by 2 to get 4p, and the 16 by 2 to get 32. And then we just need to sort of group the terms. If we take the 3p to the other side, we would get a p over here, a single p, and the 32 comes to this side to make a minus 32, and then spinning those around to get p equals minus 32, and that is the answer. Not easy, that one, definitely more challenging than the perpendicular question, which is quite a common question. The parallel question is less popular. I'm not going to lie, I think this is one of the worst graph transformation questions I've ever seen, but let's go with it. So in the first part of the question, we've been asked to find the a value. So this is our original function, f of x. This is our transformed function. We can see there's two transformations that have taken place here. So the a value moves the graph vertically, either up or down, not stretching it, so it's moving it up or down, preserving the shape. The k value does stretch it vertically, so we're only making changes here to the y coordinates. There's nothing happening to the x coordinates, which would be a change in here or a change in here. So these are both vertical transformations. So what we've got to do to answer these questions is examine the coordinates. So on the original graph, the point 0, 0, the origin has been given, and the point 2, minus 1, and we're going to compare these to the transferred points. The challenge with this question is both of these do act in the same direction, so they kind of play into each other. So what I'm going to do for part A to find the a value is to examine the 0 and the 3. We don't really need to examine the x coordinates here because these are not translations or any kind of movement in the x direction. They're only in the vertical y direction. So focus in on these 2 points. So on the original graph, we've got the point 0, 0. This is part A. So we've got the point 0, 0, and that gets transformed into the point 0, 3. Now, it's obvious by looking at the graph that they've taken the original f of x function and it's been flipped. So the fact that it's been flipped or sort of inverted, sort of mirrored across the x-axis, tells you the k value is going to be negative. It's also being stretched. So the k value is going to be negative and it's going to be a value greater than 1. So it's been stretched and flipped at the same time. So that's kind of almost two transformations in one. So this is a little tricky. But anyway, this value is not massively affecting part A of the question, where you can see that the y coordinate has gone from 0 to 3, so it doesn't matter what stretch you apply to 0, it still becomes 0. So that tells us that we can almost ignore, well, we can ignore the k value when trying to find the a value, because the 0 here, even if you stretched it, like say the k value was 4, 0 times 4 is still 0. So any change between the 0 and the 3 here must be a result of the a value rather than the k value. So that just simply tells us that the a value equals 3. And notice that question is just a state question. There's no working. It's just about knowing how the graph transformations work. But it's a little bit icky, right? It's just not a very well designed question in my opinion. So that gives us anyway the a value, which is 3. So keep in mind that we now know that value, so we can now use that value, if you like, in the part B of the question. I'm just going to do that over here. So in part B, I'm going to compare. Part B is to find the k value. I'm going to compare the other points. So again, we're only focusing on the y coordinate. So in the first question, part of the question, we focused on these two. I'm going to now focus on these two, -1 and 5. So it should be that if we take this original value, -1, and apply the transformation to it, we should get the value 5, because that's what the transformation does. So it should be that if we take this sort of formula, which is k times the f of x value. Well, the f of x value is just a y value, so that is -1. So we're sort of putting that -1 in as our starting value. So k times -1 plus the a value. Well, we know that a value now is 3, and that should come out to be 5, because if you take the original coordinate, apply the transformation, you should get this new coordinate. So we're basically taking that information, turning it into a little equation to solve to then get the k value, and this should now be fairly trivial. K times -1 is -k, plus 3 equals 5, and then minus k would equal 5 minus 3, which is 2, so that implies then that the k value is -2. Now we expected it to be a minus because if you've got a value here, that would basically make all the y coordinates on the original graph the negative of what they are, which has a net effect of flipping the graph, either flipping it over the x-axis, so that should have been a negative, and also the fact that it's been stretched by a factor of 2 makes sense in terms of the graph. You can see the graph has been stretched as well as being flipped. So that's how we go about finding the k and the a values, but definitely a slightly icky question, and like I said, just not one of my favourites. In this question, we've been asked to evaluate this definite integral, and it looks quite intimidating. So if you check on the formula sheet, there are some integrals for trigonometric functions, and on the formula sheet it's written that the integral of a simpler form, cosine ax dx, is equal to 1 over a times positive sine ax plus c. But that formula can be a little misleading because it just seems that whatever number goes here goes here. That can be true, but actually what's happening is that this here differentiates to a, and it's the a that goes down there. So when we come to apply this formula to our question, you can see that the form here and the form here are not identical, so it's knowing how this actually works is really important. In other words, for us, the derivative of the inside of this bracket is just 3, because if you differentiate 3x minus pi by 6, well, pi by 6 is just a number, so when you differentiate a number, it goes to 0, and that's going to be really super important and the key to unlocking this question. So let's get into that. First of all, are we in an integratable form? Always got to check that it is in an integratable form, roughly in this form here. There's nothing to deal with. So we can go straight into our integration. Remember, this is a definite integral, so we're going to be putting the sort of solution to the integral in a square bracket. So let's just check this. Cosine we know integrates to positive sine, and this 1 over a is 1 over the derivative of the inside of this. The derivative of the inside of the bracket is 3, so in our case we're going to get 1 over 3, 1/3, times sine, and the bracket itself never changes, so the ax here stayed as ax. Our bracket will stay as 3x minus pi over 6. So that is our integral, and we're going to be evaluating that between the limits 0 and pi by 9. So remember, because it's a definite integral, you don't need a plus c, no constant of integration. So now it's just a case of subbing in the value. So we've probably got a mark already at this point, but we need to now sub in the value. So really now it's no longer an integration question, it's more of a trigonometry, so trig exact values or something like that type of question. So subbing in the values and being very careful, I think, with these. So I'm going to keep a square bracket just to separate out my terms. So when I put in the pi by 9, I'm going to get 1/3 sine. So this bit here is going to be 3 times pi by 9, which is 3 pi by 9. So I'm just going to write that as 3 pi by 9. So all I've done there is replace the x with pi by 9. And we're going to be subtracting from that pi by 6. Okay, and I'm just going to use a square bracket to keep that tidy from the second limit subbed in, which is 0. So it's going to be 1/3 times sine of 3 times 0 is 0 minus pi by 6. So be really careful when you're doing definite integrals, which have got a 0 limit, to not assume that the whole bracket will go to 0. That is true for polynomial functions, and if you've worked a bunch of those, you might be used to seeing a lower limit of 0 and this whole bracket just going to 0. For trigonometric functions, that doesn't always, in fact usually doesn't happen, so be really careful to work this all the way through and not just write this one off and say it's going to be a 0. So we've got a bit of work to do now, a little bit of simplifying. So if you look at these here, so 3 pi by 9, might just do that as a little bit of side working. So 3 pi by 9, well, we can simplify that top and bottom to make it just pi by 3, and we're going to be subtracting from that pi by 6, so it's minus pi by 6. So this will be minus pi by 6. So we want to combine those. So we could make this pi by 3 into also a denominator of 6 by making it 2 pi by 6. So 2 pi by 6 and pi by 3 are the same thing, and you can check yourself to make sure that that seems correct. 2 pi by 6 minus 1 pi by 6 is just pi by 6. So not easy, a little bit of tricky fraction, radian stuff going on there. So this just becomes 1/3 times the sine of this inside of the bracket is now just pi over 6. Okay, like this. And we'll do a similar thing with the second bracket, a little bit easier. So we've got 0 minus pi by 6, so that's going to be the sine of negative pi by 6. Okay, like this. So there's a rule that says if you've got the sine of a negative value, so if for example you had the sine of minus some value a, that is equal to minus the sine of a. And you can think about that from the symmetry of the graph. If you draw a sine graph and think about how the values go in the positive and the negative direction, so we normally draw our sine graph going forward like this, but it also, you know, goes back the way in the same values, same way. So if you've got sort of a value up here, there's a corresponding value for that back the way down here, and that's reflected in this little formula. So that tells us here then that the sine of negative pi by 6 is equal to minus the sine of pi by 6. So we could actually take our negative out of there. You could write this as another line of working, but just to save the line of working, and we could then pop the negative into here. But if I end up with a negative in here, that just becomes a minus minus. So I can actually pull that negative from there to here using that formula, and then from here to this negative to make that a double negative, otherwise known as a positive. So now we've got 1/3 sine pi by 6 plus another third sine pi by 6, either of the same terms. Adding those together, we're just going to get 2 of those, so 2/3 sine of pi by 6. This is a non-calculator question, so you need to be able to evaluate sine pi by 6 using trigonometric exact values. Pi by 6 in degrees is 30 degrees. This is the sine of 30 degrees. Sine of 30 degrees is 1/2. You should know that off the top of your head, hopefully. So this becomes 2/3 times 1/2. These 2's would just effectively cancel, so the final answer there is 1/3. Notice that we don't need to write in units squared, even though it's a definite integral. The question is just to evaluate the integral. It's not representing, in this question, an area, so you don't always need to write in units squared. It's only if you're representing a shaded area. In this case, it's just to do just evaluate the integral, so we're fine to present the final answer as just 1/3. Challenging question, that one, quite a lot of stuff going on, both in terms of integration and the trigonometry. In this question, we've been given these two functions, f of x and g of x, and we're asked to do a couple of things with them. The first is to find the composite f of g of x. Composites are fairly straightforward questions, so we're being asked to make f of g of x, which means that the g function is going inside the f function. Remember, f of g of x and g of f of x, the other way around, don't necessarily give the same answer, so we need to be careful to get the order correct. So good practice to just write this as f of whatever the internal function is, which is 5 minus x, so f of 5 minus x. And then to process that, we just now look at the f function, and wherever there's an x in the f function, there's only one x in this case, but there could be multiple. Every instance of an x, we're replacing it with 5 minus x. So this just becomes 1 over the square root of no longer just x, the square root of 5 minus x, and we're done. So quite simple, not a lot of work in that, and that's why it's a low marked question. So we're done with part A, we've made our composite. In part B, we're asked to take this composite, f of g of x, and find the range of values for which it's undefined. So the first thing to pick up on there is a range of values. That means that our solution is not going to come out to be a single value. It's not going to be like x equals 2 or x equals 8. It's going to be a range of values, so x between 1 and 7 or x greater than 12 or some range of values. So basically like a whole range, not just a single value. So let me just pull this over here. So we now know that f of g of x is equal to 1 over the square root of 5 minus x. So what do we mean by undefined? Undefined is a domain reference. So we're looking for the domain, looking at the domain of this function. We're looking for the values that are not in the domain, the values for which this function doesn't work. It breaks down, there's some kind of problem. There's only two potential problems. Dividing by 0 is one of them because that's an undefined operation. In other words, it would give you an error message on the calculator. And square root in a negative number is another potential issue. Both of those are potential issues in this question because we've got a square root and we've got a fraction. So let's just think about that. So we want to avoid those two scenarios, but actually in this question, we're looking for the values that cause the problem. So we don't want to avoid them in this case. So we're interested in the denominator being 0. So let me just kind of make a little note of that. We want, in a sense, to answer our question, the denominator, square root of 5 minus x, so the whole denominator. We're interested in where that's equal to 0. If it was equal to 0, you'd have 1 divided by 0, which is the undefined operation. That's what we're trying to track down. So that's our first kind of thing to think about. Just notice that an implication of that would be, let me just write it here, this would imply if you square both sides to get rid of the square root, you would have 5 minus x is equal to 0 squared, which is still 0. So these are both valid. We're maybe going to use that one in a moment. And then the second criteria would be where we try and take the square root of a negative number. You can't square root negative numbers. That's our second undefined operation in this question. So we're actually interested in the part which is under the square root, 5 minus x. We're interested in that being less than, strictly less than 0. Equal to 0 is okay. You can square root 0, you just get 0. But if 5 minus x is anything strictly less than 0, like a negative number, then you cannot square root a negative number. So these are our two issues. These are the places where this undefined part would come into play. So we've got 5 minus x is equal to 0, and we've got 5 minus x is less than 0. We could combine those, couldn't we? And we could just rewrite that little equation as 5 minus x is less than or equal to 0. So just merging our two criteria. And what has that given us? It's given us an inequation to solve. If we solve this, we will get our range of values. So the range of values always come from inequations because that's what a range is. It's basically a sort of set up as an inequation. If I move my minus x to the other side, then I'm going to get 5 is less than or equal to x. And then you could just spin that around to say that x is greater than or equal to 5. Just be careful to keep the x on the open end, so the x is still on the open end. So that is our solution, that is our range of values. So what is that saying? That's saying that if x is greater than or equal to 5, that is going to lead to this function being undefined. Let's just quickly check that. So if x is equal to 5, you would get 1 over 5 minus 5 square rooted. 5 minus 5 is 0, the square root of 0 is 0. That scenario would lead to 1 over 0, which is undefined. If x is bigger than 5, so like 7 for example, then you would have 5 minus 7, which is negative 2. Square root of negative 2 is undefined. So these are the values that are going to lead to the function being undefined, the values for which the function is undefined. In the first part of this question, we're asked to find cos P and cos Q. So we're going to be using SOHCAHTOA for this. It's a slightly complex looking diagram, but let's just take those one at a time. So if we want to find the cosine of P, we're just going to be using, so this is part A, part 1. We're just going to be using SOHCAHTOA. So cosine is adjacent over hypotenuse. So looking at our reference angle, adjacent is this side here over hypotenuse. So we don't have the adjacent side. This is missing. We're going to have to use Pythagoras. So using the root 5 and the 1 and calling this little b, we would have that 1 squared plus b squared, so calling this side we're looking for here little b, this one little b, is equal to the hypotenuse squared, so root 5 squared. That's just setting up the Pythagoras equation. We're going to try and solve it for b. So 1 squared is 1, so that's going to be b squared. Root 5 squared is just 5, the square root and the squared cancel. So this guy becomes 5, and that 1 that we've got here moves to the other side as a minus 1. So that's going to be 5 minus 1 is 4, square root in both sides, and you'll get b equals the square root of 4, which is 2. So a little bit of Pythagoras, which is really common in this question type. So I can now scrub this out and put in a 2 there. So we know this triangle is 1, 2, and root 5. So the cosine of P adjacent over hypotenuse, that's going to be 2 over root 5. Okay, and then part 2 of the question, we're doing the same thing, but we're trying to work out the cosine of Q. So switching to the other triangle and the other reference angle, this is a Q there. It looks a little bit like a 9, but it's meant to be a Q. So this time our reference angle is here. So this is opposite, adjacent, and hypotenuse. The adjacent is all of this length here, so it's going to be the 1 that we're given and the 2 we've just made, so the total length here is 3. So the adjacent side here of this triangle is 3, and the hypotenuse is this side here, which is root 10. So it's going to be 3 over root 10. So pretty typical, having to do Pythagoras and then a little bit of SOHCAHTOA, and sometimes with the orientation of the triangles that can be a little tricky. So next part, the main part maybe, I guess you could say, of the question, part B, we're trying to find the sine of P plus Q. So the challenge with this question is recognizing how to get started. P plus Q, sine of P plus Q, or sine or cos of anything like this, bracket with a term plus a term, that you need to recognize as being in the format for the addition formulas, which are on the formula sheet. So this will expand as sine P cos Q. For the sine expansion, the plus stays as a plus, and then it's going to be cos P and sine Q. So the formula sheet is written not with P's and Q's, but A's and B's, but just updating for the letters are actually in your question. So we've got cos and cos. We've got these two guys here, so we can plug those in a moment and then help us evaluate. But we don't have the sine P and the sine Q, so we're gonna have to make those. So I'm just gonna maybe write those up here. So the sine P, again, just using SOHCAHTOA, so turning back to P as our reference angle. Sine is opposite over hypotenuse, opposite is 1, hypotenuse is root 5, so sine P is just 1 over root 5. And then we're gonna work out the sine of Q, which is the last thing we need. Turn into Q as a reference angle, the opposite is 1, the hypotenuse is root 10, 1 over root 10. So that means that we've now got all 4 parts that we need. We can just start plugging those numbers in. So just putting them in the correct order, obviously. So sine P is 1 over root 5. These are multiplying together, so it's good practice maybe just to use a bracket to imply the multiplication rather than using a multiply sign, which tends to be a little messy. So cosine of Q is 3 over root 10, like this, and then just carrying on. So the cosine of P is 2 over root 5. And then finally, the sine of Q is this one here, 1 over root 10. In these questions, you should find some kind of symmetry. So it's pretty typical because of the nature of sine and cosine, having the hypotenuse on their SOHCAHTOA expansion, so A over H and O over H, it should be that you've got consistent denominators here. If one of these was randomly like a root 7, then that's clearly not going to be right. So just multiplying these together, they're fractions, you're multiplying fractions, so multiplying the 2 tops and the 2 bottoms, so 1 times 3 is 3, root 5 times root 10 is root 50, okay? Same over here, 2 times 1 is 2, so we're going to get plus 2 on the numerator. Root 5 times root 10 is again root 50. These have got the same denominator now, so we can just go ahead and add them together. So 3 plus 2 is 5, so it's going to be 5 over root 50. You might be done at that point in some questions, it just depends. In this case, we can simplify because root 50 can be expressed by third sort of simplification as root 25 root 2. So casting your mind back to the past when you did thirds, square root of 25 is 5, so that simplifies down to 5 root 2. So if this was a calculator question, which it's not, you could just put that in the calculator and hit equals or enter or something, and you would get 5 root 2. That's just the simplified form. So we can just replace the denominator, root 50, with 5 root 2. And you would see here that dividing top and bottom by 5, you're going to get 1 over root 2. Which is almost the final answer, but you'd probably be expected to rationalize that by multiplying top and bottom by root 2. So if you can't quite remember that, I'll just quickly write it in. So it's going to be root 2 times root 2, root 2 times root 2 over root 2, times root 2 over root 2. But root 2 over root 2 is just a fancy version of 1. So we're just multiplying by this fancy version of 1. But that has the effect of 1 times root 2, giving us a root 2 on the top. And root 2 times root 2 is just 2. So we've turned our 1 over root 2 into root 2 over 2, which is in the rationalized form. So that is the final answer to that question. In this question, we've got a couple of things to do. We've got to evaluate this log expression, and then we've got to solve this log equation. Sometimes in a question like this, these two parts will be connected. So taking your result here and using it in the second part. I think in this question, we don't have to do that. So we'll just treat these as two separate questions. So we're going to be using the laws or the properties of logarithms to help evaluate this. Remember, evaluate means either work out as a final numerical answer, or it can mean just like simplify something down. In this case, it will be to simplify it all the way to a numerical answer. So all log questions, you should check if the bases are the same. If the bases are different on the terms in the expression, then you cannot use the log rule. So it's a really, really important point. These questions are generally about using the rule. So the bases here are the same, so we're good to go. So the first thing we're going to do here is notice there's a plus in between our two terms. That implies you can use the rule where you combine the two logs into one with a multiplication, which we'll check in a second, but you can't do that if there's a number in front of one of the logs. So our first move will be to take the log rule that says if there's a number in front, you can put it up onto the power. So always scanning across to see what scenario you've got. So we will just keep the first term like this. The second term, we're just going to put that 2 up onto the 5 as a power. Now we've got a log term plus a log term with no number in front. We will be able to use the rule for that in a second, but before we get there, let's just simplify the second term by processing the 5 squared. 5 squared is obviously just 25, so that becomes log to base 10 of 25. So at this point, we've got these two nice, neat log terms, and this falls into the sort of form where we can say log plus a log. Like this, we can merge into one single log term, keeping the base of 10, and we're going to get 4, this bit in here, I'll just write it, is going to be 4 times 25, okay? So that's how that rule works. If it's a plus, you make it into a times. If this was a minus, you make it into a divide. So this is going to become the log to base 10 of 100. And when you get a log expression like this, it's really just asking you, what power do you need to put on the base to make this number? So what power do we need to put on a 10 to make 100? That answer is 2. So you don't need any more working. The answer is just straight to 2. That's all you need to do. It's the opposite of an exponential. In other words, this is telling us that 10 to the power of 2, where 2 is the exponent, 10 to the power of 2 equals 100, so the answer there is just 2. So moving on, we're going to be using similar rules maybe in this question. So here we've got the log of something, an expression minus this log. They've got the same bases. There's a minus in between, so we can combine them in a similar way to how we combine these two here. But because it's a minus, this time we're going to be combining them in a slightly different way. So it's going to be log to base 2, not of a product of these two, but as a quotient, which will be 7x minus 2 divided by 3, like this. And that's going to be equal to 5. Okay, so at this point you want to get rid of the logarithm. There's a couple of different ways to do this. You can introduce a log on the right hand side, but basically this is just needs to be rearranged. The way you rearrange it is you just take the base number, which is 2, and apply this as the power. So 2 to the power of 5 is going to be equal to 7x minus 2 over 3. You might have learned that as introducing a log on the right hand side. You get the same answer either way. But I like to think of it like this. If you've got the example 2 to the power of 3, 2 cubed is 8, that's an exponential expression. That can be written in the same way of connecting these numbers as a logarithm by writing log to base 2 of 8 equals 3. So in our question, we had this scenario here, which was like this one, and this would turn into this like that. And in the same way, we've turned this into that. So you'll see that that move from there to there, and the move from there to there are just the same thing. That's really just something you need to learn how to do. Or like I say, there's another method where you introduce the log on the right-hand side, make it log to base 2 of 2 to the power of 5, but you would end up just with a 2 to the power of 5 anyway. So it doesn't really matter which way you do it. Anyway, carrying on, at this point we've gotten rid of the logarithm, so we're just solving this as a normal linear equation. 2 to the power of 5 is 32, so that's 2 times itself 5 times. I'm just going to spin this around to put my variable on the left, so I'm going to write 7x minus 2 over 3 equals 2 to the 5, which is 32 like this. Multiplying both sides by 3 to get rid of the fraction, so we're left with 7x minus 2 on the left. 32 times 3 is 96, I think, yeah, 96. And that would be 7x equals 96 plus 2, which is 98. Hopefully at this point it divides. If it does divide, that kind of suggests we've done it right. This will divide to give us 14, and that is the final answer for that equation. In this question, we've been asked to solve the trigonometric equation sine 2x plus 6 cos x equals 0. So always important to check, are you in radians or degrees? Is it calculator, non-calculator? That's really going to define how you go about solving the question. So we're in degrees and it's a non-calculator question, and the range of values is 0 to strictly less than 360. So you've got to be careful with this range of values to see what's included, what's not included, and we'll check in with that again later. Pretty typical scenario here, a double angle term and a single angle term. You can only solve for one or the other, so we need to change one of them into the other. We're going to change a double angle, which is how we always go about these. So from the formula sheet, sine 2x becomes 2 sine x cos x. So it's written with a's on the formula sheet, but just updating to use x because that's what is in our question. So sine 2x is 2 sine x cos x. And then the other term we're just going to leave alone, so 6 cos x equals 0. So we've gotten rid of the double angle, and now it's just a case of factorising and then solving. So we can factorise here using a common factor of 2 cos x, that's the highest common factor, so putting the 2 cos x outside a bracket, and then we would need a sine x term, and we would need a 3 like this. So this is just like when you're factorising with a normal sort of x terms, you know, like a quadratic equation, that sort of thing. And now we could just separate into two equations. So we get 2 cos x equals 0 from this term, and then we get sine x plus 3 equals 0 from the inside of the bracket. I'm just going to deal with this guy first, because if you rearrange that to get sine x equals minus 3, well, negative 3 is outside the range of sine. So sine, if you think about the sine graph, it only goes between minus 1 and 1, so there's no solutions to this. The sine graph never gets to minus 3. So just to quickly highlight what I mean there, so the sine graph goes like this, and the lowest value, the minimum value, is minus 1. Negative 3 though is way down there, so if you draw a line horizontally across, you would never touch the sine graph. So there's no solutions to that part of the equation. So you can just write that as no solutions without any explanation really. Turning back to the other one, dividing both sides by 2, we're going to get cos x equals 0. And then how you go about this would depend on the values here, but for these extreme values, as I like to call them, so 1, minus 1 and 0, it's best to think about those off of the graph. So if you think about the cosine graph, it's the sine graph moved over a wee bit, so it looks basically like this. So we want to know whereabouts on the graph does it get to 0, but remember that means 0 up and down the way, not 0 along the way. So it gets to 0 up and down the way, like up and down as in 0, 1 and minus 1, here and here. So what are those points? Well, those points are at 90 degrees and at 270 degrees. So the x solutions there are just 90 degrees and 270 degrees. If you were in radians, you would just write the radian equivalent of those values. Okay, so those are our two solutions for part A. Turning to part B, notice that part B is a hence question. In other words, use your result from part A. And also there's only 1 mark on offer, which seems weird, right? Given that the question looks quite complex. But if you notice, there's a strong connection, isn't there, between this equation and that equation. So what's happened, all that they've done is to double the angle. So this 2x has become a 4x, this 1x has become a 2x. So if you think about what happens if you take a sine graph and then change it to a sine, a sine x graph and change it to a sine 2x, the 2x graph gets squished, doesn't it? It gets compressed. So what that really means is all the x values are being halved. So the solutions to this equation are just the solutions to this equation halved. So we can just go straight to saying that because there's a solution here at 90 degrees, there's going to be one here at 45 degrees. Because there's one here at 270, there's going to be one here, which is half of that, which is 135 degrees. And that could be the question done. But what you've got to think about is if you're halving values, are there values which are not picked up here, but which when you half them would still be in this range here? And the way you're going to do that is because every point on a sine or cosine graph recurs every 360 degrees, like the value of the period. That's what the period means. It keeps recurring every 360 degrees. So if you take 90 and add 360 to that, which I'll just, well, maybe just do over here actually. So if you take that solution 90 and we add on 360 degrees, that's going to give us 450. And that would be the next solution over here, but that's outside the range. But on this scenario, we're going to be halving that. So if we divide that by 2, we're going to get 225. So these are sort of our two primary solutions, but we're going to get more. So the next one would be at 225 degrees. The next one here would be 270 plus 360. Okay, so just quick bit of mental math there. It's 500, 600, and 630, I think. Okay, and then that's obviously way outside the range, but if you half that, you're going to get 315. So 315 is in the range. So that second part of that question, i.e. getting these two values, is quite complex, it's quite tricky. You've got to think of solutions that didn't appear in the first part because they were outside the range, but which appear in the second part of the question because you're halving them to get them to like suck them back into the range. So it requires a bit of imagination. So those ones not too bad, those ones quite challenging. In this question, we'll be given this circle and we're given this point P, and we're asked to show that the distance between the center of the circle, C, and point P is given by the weird looking expression in the question. So the first thing we should do is to identify the center of the circle. So remember that in this basic circle equation, this number here and this number here help you to get the center point. So the center here is going to be 1 and then negative 2, because the native form of that equation is minus a and minus b, so that's why this has to be a minus 2 center point to get the plus 2 in the bracket. So these are the 2 points that we're interested in, and in part A of the question we're trying to make the distance between them. So the distance formula, which is not on the formula sheet, is basically Pythagoras. It's given by the square root of the difference between the x coordinates squared plus the difference between the y coordinates squared. So you can think of this, if you wish, as being x1 and y1 and being x2 and y2. So it's quite good practice to sort of label them like that. And then you can just go ahead and plug into the equation or the formula. So our x2 is 1. So we're going to get 1 minus our x1 value, which is 4. Doesn't matter, by the way, if you make this x1 and y1 or x2 and y2. It doesn't matter on the allocation like that, as long as you're consistent with the way you do it. So then y2 here is negative 2 and y1 is k. So it's going to be like this. Okay, and then we can just carry on from there. So this is going to be the square root of, so 1 minus 4 is negative 3. Negative 3 all squared, which is negative 3 times negative 3, is going to give us positive 9. This one here is a little bit fiddly. It might have been better the other way around, actually, to make it k minus minus 2, but it doesn't really massively matter. So if you just think about those brackets, so minus 2 minus k squared, well, a bracket squared just means the bracket times itself, so it's like this. And then you've just got to multiply that out using normal sort of FOIL technique. Minus 2 times minus 2 gives us 4, and minus 2 times minus k is going to give us plus 2k. We're going to get another plus 2k from these guys multiplying, and then the minus k times the minus k gives us a positive k squared. I'm just going to spin these around to give me a k squared. 2k plus 2k is 4k plus 4 like that. So this is going to become 9 plus k squared plus 4k plus 4. The 9 and the 4 would combine, and then I'm just going to reorder this as like a trinomial to make it k squared plus 4k plus 13. So I can see in that question, I maybe never made the best allocation. I might have been better to make this x2 and y2 and this x1 and y1, because that made it a little tricky over here, but it's quite a small difference really. You're still doing the same process. So that's where the value comes from in part A of the question. And then in part B of the question, you've got to think about how these parts are linked together. Keeping in mind that this here, this d, this distance represents the distance between C and P, the point C and P. And in part B of the question, they're saying, imagine that point P lies outside of the circle. Well, if it lies outside of the circle, so let's imagine we've got our circle here. That's pretty decent effort there, a circle. So you've got the center point here. See, if point P lies, say, here, which is outside of the circle, well, that implies that the distance between C and P has to be greater than the radius, because that distance there is the radius of the circle. So C to P is clearly bigger than that radius value. So that says that the distance has to be greater than the radius. So the distance has to be greater than the radius. Well, we know the distance is given by this thing here. So that's going to be the square root of k squared, just the same thing we've got here, k squared plus 4k plus 13, that has to be greater than the radius. At the moment we don't have the radius, but remember in this basic form of a circle equation, this number on the right hand side represents the radius squared. So if the radius squared is 25, then the radius is 5. So that has to be greater than 5. So not easy that, a bit of logic required there, a bit of visualization maybe, and now we've got an inequation to solve. Because it's an inequation, that's why the question has been worded to find the range of values rather than find the value, because it's an inequation, not an equation. Okay, so we can start by getting rid of the square root by squaring both sides. So that's going to give us k squared plus 4k plus 13 is greater than 5 squared, which is 25. And we're going to want to form this into a trinomial. So we can form our trinomial by taking the 25 over. So we get k squared plus 4k, so it's going to be 13 minus 25, which is minus 12, is greater than 0. We need to factorize this into two brackets like this. Remember that this is a quadratic inequation. This one, oh, by the way, will factorize with a 6 and a 2, positive 6 and a negative 2. It's not a quadratic equation. Quadratic inequations are more difficult to solve. You don't just necessarily separate them into two equations. You need to think about the roots here. So if we solve those equal to 0, the two roots would be k equals, you would get a negative 6 from that one and you would get a positive 2 from the other one. So this is a little bit of side working. This is only for quadratic inequations. If this was an equation, those would be your final answers. So what you have to do then is remember that this basically makes a parabolic shaped graph. These are the roots of the graph. So if I mark on negative 6 there and positive 2, this is imagining this to be the k-axis. It's a positive k squared term. So that means that the parabola would be shaped like this, like a U shape rather than an upside down U. And we want to know where our parabola, where our quadratic is greater than 0. Greater than 0 means above the axis, above the k-axis in this case. So it's the graph there and it's a graph there. So it's all the k values going that way and all the k values going that way. This point is at 2, so it's all the k values greater than 2. This point was at negative 6, so it's all the k values less than negative 6. So you really need the roots and the sketch of the parabola to solve this. You can't really do it algebraically at the end. You might get lucky and get it right, but really it has to be done with this justification. So the final answer here is that k is less than negative 6 and that k is greater than 2, and that is the range of values that satisfies the condition given in the question. Quite challenging, that one, a little bit more into the realm of problem solving. So in the first part of this question, we're given this trig expression and we're asked to write it in this form here. So it's not obvious what to do in this question. It's not a standard question type, but if you've ever got a bracket squared, then that really just means the bracket times itself. So I'm just going to pull this down and rewrite it. So we've got sine x minus cos x, all of that being squared. So something being all squared just means really the bracket times itself. So that's effectively saying sine x minus cos x in one bracket times the same bracket, sine x minus cos x. So by doing that, we've now got it in a form where we can just multiply out the brackets, so using FOIL. So sine times sine gives you sine squared x, then you're going to get a minus sine times cos, so minus sine x cos x. You're then going to get another one of those, another minus sine x cos x, and then finally you would get minus cos times minus cos, so a double negative to give you a plus cos squared x. Still not obvious what to do, but we can certainly simplify by recognizing those are just the same thing. And I'm also going to reorder by putting these two together. So you should recognize sine squared plus cos squared. It's a trig identity you're meant to know. So minus sine x cos x minus another sine x cos x is minus 2 sine x cos x, like that. Okay, and there is a little bit of sort of creativity and imagination in these. They're not easy questions, but this is a formula that you're meant to know. Sine squared x plus cos squared x equals 1. So all of this just equals 1. So if you imagine sort of grouping those together, that just equals 1. So that's going to become 1, and then we're left with minus 2 sine x cos x. If you look on the formula sheet though, 2 sine x cos x is just sine 2x, or it's written with a's on the formula sheet, but 2x. So this just becomes 1 minus this whole thing here is just sine 2x. So looking at the form we were asked for, you can see that the 1 is playing the role of p, the 2 is playing the role of r, the q is a little bit less obvious, but this is basically the number minus 1 in here. So it's minus 1 times sine. So it's the plus q is actually a minus 1. So we've met the criteria, but not easy. These trig identity questions are quite challenging. So you need to know the rules, you need to know what to look out for. So anyway, we've turned this expression here into this expression here. We're going to need that for part B because we're asked to evaluate the indefinite integral of this. This is definitely not a form that we know how to integrate. There's no rule we can obviously apply, but we've just learned in the first part of the question that that and that are the same thing. So we can change this to the integral of 1 minus sine 2x dx. That then puts it into a form that we do know how to integrate. This is just a single constant term. This is a trig term, which are on the formula sheet. So we can just integrate those term by term. When you integrate 1, it goes to 1x, or just x. When you integrate sine integrates to negative cosine. So we're going to get a negative negative, which will become a plus. And we bring the 2 as a 1 over 2. So that's just a direct match to the formula sheet. On the formula sheet it's written as sine ax, and it becomes 1 over a minus 1 over a cos ax. So this will just be a 1 over 2. The minus minus makes a plus, and this becomes cos 2x. Because it's an indefinite integral, we need to put our plus c on the end. And that's all you can do there. It's a funny sort of function. You can't really combine any terms. So that there is the final solution.